For Module 3, I'll be focusing on the general linear model, multiple regression and correlation, and ANOVA. My hypothesis for this module is, does social motivation predict reward-seeking behavior in an autism sample? And our null hypothesis is that social motivation does not predict reward-seeking behavior. The general linear model is an equation of a line that demonstrates independence between the dependent variables and all independent variables or predictor variables. It rests on the theories that x and y are linear, that there are no errors of omission or measurement, that all variance is homogeneous, or that there's no multicollinearity between variables, that the average model error is equal to 0, that the dependent variable is uncorrelated with any error, and that all error is normally distributed. Both multiple regression and ANOVA uses the same equation. So as you can see at the bottom of the slide is the equation. Y is the dependent variable or the outcome variable that we care about. B naught is the intercept of the line or the y value of all independent variables, plus bx, which in multiple regression is all of our covariates. And in ANOVA, this is all our class level nominal variables or factor variables. And then plus error, we use error in ANOVA. This is based on the Platonic essentialism theory that the essence of perfection exists. Thus, error, we use anything that's not perfect is used as error. In multiple regression, we use residuals. So any interaction or difference in means with variables will be called and termed as residuals. This is the portion of the data set that I'll be running diagnostic analyses on. Of note, y1 is our outcome variable or dependent variable. y2 through y4 is our independent variable or predictor variables. These are my variables that I am testing. There's one dependent variable that's reward-seeking behavior, and then anxiety, social motivation, and social cognition are independent variables. And to the right in tabular form, we have a correlation matrix. This looks at the intercorrelation between each of the variables. And of note, y1 and y3 are highly correlated at 0.79. Anything above 0.7 in behavioral sciences suggests that there probably is a measurement error. So multicollinearity increases the standard error. This increases the t-value of our signal-to-noise ratio, and a tool we can use to see if multicollinearity is the reason that we're failing to reject the null is called the variance inflation factor. So the variance inflation factor tells us how much multicollinearity is inflating each standard error in the model. And as you can see, we have an effect of collinearity with our variables, but not to the degree that it's inflating or driving our decision solely based on multicollinearity to reject the null hypothesis. Here we have run a simple regression model, and this tells us how much of the variance of the dependent variable of reward-seeking behavior can be explained by each independent variable. And that is measured in r squared of coefficient. And that's in the left column of our estimate. So the intercept of our line is met at 0.12. Both anxiety and social cognition, or y2 and y4, are negatively correlated with our dependent variable. However, social motivation, or y3, can strongly explain the variance seen in reward-seeking behavior. And if we run the estimate of what we expect. Against the standard error of each mean, we get a t-value of 6.620, and this is significant at the 0.001, less than 0.001 level. Cortina's 2002 paper stated we can reject or fail to reject the null hypothesis. So in this case, we can reject the null hypothesis. You do not accept the null hypothesis as stated in their paper. Our multiple R squared altogether, so that's all the independent variables, looking at how much of the variance of the dependent variable can be explained by them altogether, is 0.636, and that's on a scale of 0 to 1. The general linear model theorizes that all errors or residuals are normally distributed, and a good way to visualize normal distribution is to run a histogram, make a histogram plot, and you see in this graph that we do see some violation of assumptions in that these residuals are not normally distributed. The general linear model also theorizes that there is a homogeneity of variances between each residual, and that the difference in means of each residual is equal to 0. As you can see, here's another graph that shows a violation of assumptions, as the variance of our residuals seem to be spread out and not on this horizontal line that would represent homoscedasticity. And we do see some potential outliers, in particularly data point 14 might need to be further looked at. To test that our residuals have shared common variance, or to test the residuals assumption in the general linear model, we can use these graphs, in particular the residuals versus fitted graph on the top left. If the red line is close to the dotted line, we can assume normal distribution. As you can see, there is a lot of overlap between the dotted lines and the red lines, and that tells us that we might still have a normally distributed model. However, I want to also draw attention to the bottom right graph that shows Cook's distance. Cook's distance is a tool that acknowledges or points out some potential outliers in our data set, and data point 14 seems to be standing out as a potential outlier. Here is an analysis of our Cook's distance model. You can see in the bottom, our mean of Cook's distance is 0.04. And the graph shows that there does seem to be an outlier, data point 14 in particular. However, Cortina strongly cautioned against taking out outliers for the sole purpose of catering to your hypothesis, because it might reveal bias. So we're not going to take it out. We're going to leave it as is. Also, the mean of the Cook's distance model doesn't rise to the level that suggests this requires further investigation. ANOVA largely refers to analysis of variances and looks at the differences of means between groups in factor class level nominal variables. Here I ran a t-test and f-test between the variable reward-seeking behavior and our class level variable sex. Gary King referred to in his paper that ANOVA and the difference in means have been credited with requiring less restrictive assumptions about the data. Some think ANOVA can be used with dichotomous dependent variables, and others say ANOVA can also allow for dichotomous independent variables. So when we ran our f-test, we see that the difference in means had an effect but was not significant at the 0.5 level when comparing differences of means of reward-seeking behavior and sex.